Hello, and welcome to this lesson on estimating irrational numbers without a calculator. So say goodbye to your calculator. Now, we would like to be able to estimate a bunch of irrational numbers. Mostly it's going to be square roots. Okay, so don't freak out too much about some of the problems. Our essential question says, how do I estimate irrational numbers without a calculator? I guess we'll figure it out. Did you know that a perfect square is a number that is the result of a number multiplied by itself, and that should be a whole number multiplied by itself. So if I had something like 3, I should get the right tool out, huh? 3 times 3 is 9. 9 is considered a perfect square. It's also because only perfect squares can make a perfect square with that many objects. For example, if we had 9 objects, 9 Cheerios or Cheez-Its or something, you could actually form that into a square. Like that. 9 is considered a perfect square because if you had 9 objects, you could arrange it. So look at this. I've got 9, and that does make a perfect square. But this doesn't work for all number. For example, if you had 12 objects, if I give you 12 Cheez-Its, could you form that into a perfect square? You can't. It would be 3 by 4. It'd be like 4 along this way or 4 this way, or that's as close as you can get to a square. You can't do it because 12 is not a perfect square. You could do it with 16. You would have 4 Cheez-Its on each side, 4 here and 4 wide, and it would be a 4 by 4 square, which makes 16 objects, and 25 and 36 and so on, because all of those numbers are perfect squares. So we do have some vocabulary. First of them is a perfect square. So a perfect square is a number that when you take the square root, it gives you a whole number answer. Square root of 9 is 3, because 3, my hand touched the thing, 3 times 3 is 9. It's the result of a whole number multiplied by itself. Now, perfect cube is very similar, but for a cube. It's a number that when you take the cube root of it, you get a whole number answer. So the cube root of 8 is 2. Because 2 times 2 times 2 is 8. And we haven't even talked about perfect cubes yet, really. We'll talk about them a decent bit in this lesson. Now, in order for us to approximate square roots and perfect squares, we have to either have a very good working knowledge of our times tables, up to about 144, so like up to 12 times 12, or at least be able to make a chart that we can keep referring back to throughout the lesson. So that's what I'm going to do. Is I'm going to make a chart here. So I'm going to make a chart of a number and then its square. So 5, 6, 7, 8, 9, 10. That was a 9. 10, 11, 12. Now, if I square each of these numbers, if I take 1 times 1, I'm going to get 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And 36. 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. And finally 144. Now, these numbers in the bottom row, these are perfect squares. It is these numbers and only these numbers in between here that if I square root, I get a perfect answer. If I'd pick some other random number between 25 and 36, every other number between here would give me an irrational answer. And I'm going to take my calculator back out to show you. Square root of 25 is 5. Square root of 36 is 6. Square root of anything between 25 and 36, 32. irrational. Square root of 28, irrational. Square root of 30, irrational. Okay? I'm going to leave my calculator up. I don't feel like actually putting it away. And I may refer to it a time or two, but we're going to try to do the math that we're doing without a calculator. So let's see here. So now that we have this chart made, we can actually refer to it at any time throughout the lesson. So it says here, for each irrational number below, estimate its value without the use of a calculator. So what I don't want you to do is I don't want you to go, okay, square root of 80, and then just rounding your answer, because rounding and estimating are not the same thing. But what we can do is we can use this and go, okay, square root of 80. I know that if I square root, say, 36, if I square root 36, I'm going to get exactly 6 as an answer. That's what this chart tells me. The square root of 36 is 6. Where would 80 fit in on my bottom row? It would fit, whoa. I've got a wrong thing in there. I had 86. That should be 64. Hopefully you were screaming at your screen because I had the wrong thing in there. My bad. Sorry. But I can see that now because now 80 would fit in somewhere between 64 and 81. But a whole lot closer to the 81 because the square root of 80 is very, very, very close. Here, I'm going to write a little bit here instead of just talking. The square root of 80 would fit like right in here if these were on a number line. I know the square root of 64 is 8. Square root of 81 is 9. So the square root of 80 is, we're going to say it is about 9. Little squiggle dude means about. That's also the same squiggle dude we used for similar figures back in the first unit. We had that same tilde. That also means about. So our answer is about 9. It is much closer to 9 than it is to 8. And actually, if I go back up my calculator, I actually did it. It was 8.944. That is very much closer to 9 than it is to 8. All right. Square root of 96. Let me change color here. Square root of 96 would fit in, well, between these two right here. It is closer to 100 than it is to 81, though. So I would put it like this, and I'd say square root of 96 is about 10. That's all we're trying to do. We're just trying to get an about answer. That's what estimation and approximation is about. We're not rounding, we're estimating and approximating. Square root of 45 on my number line fits right in here between 36 and 49. Now, is it closer to the 36 or is it closer to the 49? It's closer to 49. It's only 4 units away from that, but 11 units or 9 units away from the square root of 36. So this one is going to be about 7. And then finally, square root of 14 would fit in somewhere right in here between those two. But it's definitely closer to the 16, which means square root of 14 is going to be about 4, or much closer to 4 than it is to 3. So we're going to say it's about 4. Okay, so that's estimating with square roots. Now, I have some expressions. We are still not using a calculator, even though the expressions, they look ugly now, because we can use our brains instead of our calculator to do the same math. So letter F says 4 times this square root of 32. Now, looking at my chart up above, square root of 32 is between the 25 and the 36, but it's a lot closer to 36. So then I can estimate that this piece here has a value of about 6. And then using my brain, 4 times something that's about 6 will give me about 24. Now, I want to double check that. I mean, I know I'm right, but if I just plug it in the calculator, let's see how close to about 24 I am. That's not too shabby. 22 and a half, 22.6. That's probably a much closer guess than just a wild guess than probably what you thought we were going to get. We're pretty darn close. Okay. Square root of 38 over 3. Square root of 38 fits in here between 36 and 49. Quite a bit closer to the 36 though. So we can say this top piece has a value of about 6. And if we take that and divide by 3, 6 divided by 3 is 2, so my answer is going to be around 2. To show how close we are. We are really darn close, 2.05. Okay? Now, I would like you to try these next two, letter G and H. Again, don't use your calculator to do the work. Use your brain and your problem solving and your reasoning. When you're ready to continue, hit play and we'll go through it together. All right, so let's see. Letter G. Square root of 45 fits right in there. Wait, why am I doing square root of 45? That's not a square root. I lied. That's just 45 over. Square root of 27, though, fits right in there. And it is much closer to the 5 than it is to the 6. So I'm going to estimate the denominator here. It's about 5. And so now if I take 45 divided by 5, I would normally get 9. But because this is an estimation, I'm going to say my answer is about 9. Letter H, square root of 120. Right about there. Very, 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 very close to 121. So I'm going to estimate this piece is 11. And then when I take that times by negative 20, or times by negative 2, I'm going to get negative 22, or at least about negative 22. That was my estimation. Okay, so you're looking at your chart and you're figuring out which perfect square is this closest to. He was closest to that perfect square. So if I took the square root of 120, I'm going to get really darn close to 11. So that was perfect squares. Now, perfect cubes. Same deal, but now we're talking about a cube. So I'm going to start making my chart. And then we're going to talk about perfect cubes a little bit more. 1, 2, 3, 4, 5, 6. We don't have to go as high because these numbers actually get much bigger, much, much faster. Now, in order to find this bottom number, I'm going to take this top number, 1, and I'm going to multiply it by itself 3 times. So I'm going to take 1 times 1 times 1 is 1. I cubed 1. That is 1 cubed. 2 cubed. 2 to the third power. 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. Okay. 3 cubed. That's 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. And now we're probably getting out of your comfort zone. 4 times 4 times 4, that is 4 cubed, is going to be 64. 5 cubed, 5 times 5 times 5 is 25. And lastly, 6 cubed is, 125 is 216. Let me double check, make sure I didn't make any other mistakes. 1, 8, 27, 64, 125, 216. These all look good now. Now again, I did that without a calculator because these are no calculator questions. If I gave you this problem or this problem, you can't say, ooh, let me get a calculator to make my chart quick and then I'll stop using my calculator. No, you should be able to multiply this out. Even the 5 times 5 times 5. I just kind of told you what it was, but you can do 5 times 5 is 25. And if you need to on the side of your paper, you can multiply 25 times 5. 25, 10, 11, 12. Hey, it's 125. Okay, you can still do long multiplication if you have to. Hopefully, in 8th grade you can do this. And now the process becomes exactly the same as what we were doing before. The cube root of 150. Which perfect square is that closest to? Well, it fits in right there between the 125 and the 216. Which one is it closer to? It's closer to the 125. So I would say that that is about 5. That's as close as I can get. Cube root of 22 fits in here. That's definitely much closer to 27 than it is to 8, so I'm going to call that about 3. It's closest to that perfect square, or perfect cube, so if I would cube root it, I would get close to 3. You try the next two, very quick. Should take you 15, 20 seconds at most. Okay, hopefully you did it. Letter C here, square root of 100 fits in between those two. It's quite a bit closer to the 5, so I'd call this square root of 5, about square root of 5. And the last one, cube root. I keep saying square root. Cube root of 5 is in here. It is closer to the perfect cube of 8 than 1, so this is about 2. Fits in here. The cube root of 8 is 2, so the cube root of 5 is going to be about 2. And with the expressions, same thing. So I know the cube root of 9 is going to be about 2. Divide by 2, and don't forget my negative sign out front. I'm going to move this over just a little bit so I have space. There we go. So 2 divided by 2 is 1 with my negative out front. So this is going to be about -1. Now, just to show you how close we really are, in case you didn't even know how to type in a cube root in your calculator, the steps are this. You're going to hit 3, second, caret. If you look above this caret key, you see how it has x square root? Whatever you put in first, when I hit the 3 first, that put that 3 in that x. So that made this a cube root of 9 over 2. And I forgot my negative out front, but it's okay. I'll just throw a negative in my answer. So look at that. We said about -1, and again, I missed my negative. So that is about 1. We are really, really darn close. So that's pretty cool. We can estimate that close with these irrational numbers. Letter F, that is 6 times by the cube root of 25 is about 3. 25 is about 27. I know this gives me exactly 3, so I know this will give me about 3. A little bit less, but about 3. So when I multiply, I'm going to get about 18. That's it. Okay. I would like you to pause the video, and I would like you to try letters G and H, please. When you're ready to continue, hit play, and we'll go through it together. All right, letter G, cube root of 200. Let's change color again. Green. Cube root of 200 is, would be in there. I almost picked the wrong spot. And it's quite a bit closer to the 6, so that is about 6 divided by 3 is going to give me an answer of about 2. Hopefully you got that as well. Letter H. Cube root of 60 would be right here. That is about 4. Times by 8 gives me about 32. Now, sometimes when we're estimating, our answers will probably be off by a decent bit. This one, I'm not confident that answer is super duper close. I'm curious. 8 times 3 second caret 60. I don't think it's actually going to be super duper duper close. That actually wasn't too bad. I thought it was going to be farther away than that. So our estimation wasn't too bad. But there are times that even though we're estimating, our answers aren't going to be really close, but that's kind of okay. It's understood that sometimes our estimations will be a little bit farther away. So, solving an equation without a calculator still. Now we can refer back to those charts. Now, all of the numbers you're going to see here will be perfect squares and perfect cubes. So we solve the equation? Well, let's see. Y cubed is 27. So can you think of what number times by itself 3 times? What? So something times itself 3 times, because that's what this cube means. Times by itself 3 times equals 27. Well, if you look up in your cube root chart, what number times by itself 3 times equals 27? It's 3. 3 times 3 times 3 is 27. So we can say that y would equal 3. That would be the value that makes this equation true. Now, the official way we're doing this, I showed you how to do this using kind of more mental math. Technically, what we're doing is we are cube rooting each side of the problem. A cube root and a cube are opposite operations, and they undo each other. They cancel each other out. So this cube root and this cube cancel, and you're left with just y equals. And the cube root of 27 is exactly 3. Okay, so that's really what's happening. Now, you can do this mentally, but that's the math that's going on in the background. This one. You probably know what number times by itself equals 36. M equals 6. The math you're doing is you're square rooting both sides. But right now, without a calculator, that doesn't make much sense to us to do. It's more of kind of a mental math and understanding what you're doing. But did you know there's actually another answer to this question? Go, huh? So whenever you square root a number, remember I said that's actually what we're doing. We're square rooting here. Anytime you square root a number, you actually always get 2 answers. 6 is one of those answers. Do you know what the other one is? What other number, if you take it and times by itself, do you get 36? Something else times by itself equals exactly 36. And the answer is -6. -6 times -6 is a positive 36. So anytime you take the square root of a number, you actually technically get 2 answers. We didn't really do it up above. There are a lot of times where we kind of ignore that the negative answer exists, but there's other times we need it. Now, that is not a problem with cube roots, because -3 times -3 times -3 is not positive 27. -3 times -3 times -3 is a -27. So that doesn't really work out. It's what number times by itself 3 times equals a positive 27? The only correct answer there is positive 3. Okay? Letters C and D. I'll leave these up here for you. Why don't you pause the video, try those two. Look back at your charts we made up above if you need to help you out. I'm okay with you looking at your charts here. Or use the times tables in your head. So pause the video, try these two. When you're ready to continue, hit play, and we'll go through them together. All right, now letter C. The two solutions are 11 and negative 11. Because this one you'd have to do a square root on both sides to cancel out the squaring. X equals both of those. Letter D, this is a cube, so you would cube root both sides. That's the operation you're doing. Even if you looked at your chart and realized that H would equal 4, the operation we're doing is we're doing a cube root. A little bit uglier. Not bad, just a little bit uglier. So in order to solve this equation, we need to first, before we can do the square root like we'd want to do, because I mean, I'd love to just square root this piece, but we can't yet because this 2 is in my way. So we're going to get rid of that 2 like we would normally do. The way we get rid of a multiply by 2 is we divide by 2. And now we can square root. So now if I square root both sides, my square and my square root cancel each other out. They're opposites. I get just k equals. When I square root 16, I get 4 and negative 4. Square roots give you two answers. 4 times 4 is 16. Negative 4 times negative 4 is 16. And that's it. That problem's done. Okay, so we just added the extra step of making the equation a little bit uglier, making it a 2-step. Here, in order for me to do my cube root like I'd like to do, I have to first get rid of this plus 4. So I'm going to subtract 4 on both sides. B cubed is 125. That number's in our chart up above. If I cube root both sides, my cube and my cube root cancel each other out. They are opposite operations, and I get just B equals. The cube root of 125 is 5. And that problem is done. So we get the variable by itself before we can do any square rooting or cube rooting. Please pause the video, try these last two problems here, letters G and H. When you're ready to continue, hit play, and we'll go through it together. All right, letter G. You started by dividing by 3, hopefully. These canceled out. M squared equals 9. And now we can square root on both sides. My square and square root are opposite operations and they cancel. We get M equals 3 and negative 3. Hopefully you got them both. 3 times 3 is 9. Negative 3 times negative 3 is 9. Square roots always give you two answers. Letter H. You added 8 to both sides to cancel out this plus 8. Let's do a circle. Add 8. R cubed equals 125. And we're going to get the same answer as the one right above. So we're going to have to cube root 125, just like we did there. Cube root of this, cube root on that side. My cube and cube root cancel, and we get R equals just plain old 5. Problem solving. A couple little problem solving and we are done. So it says here, the volume of a cube. Cube, draw square, line, line, line. The volume of a cube can be found using the formula V equals S cubed, where S is the length of a side. So each side of this is S. All right. If the volume of a cube is 216, what is the length of one side? Oh, okay, so I'm going to take my formula and move it over here. It's telling me if my volume is 216, what is the length of the side of this cube? Basically, what is S? How big is each side? So problem solving. There's multiple ways of going through this problem. Way number one, you could just start thinking in your head, okay, so if it's something times by itself 3 times, what number times by itself 3 times is 216? And no, I mean, even if you're using a calculator, you can't do 216 divided by 3. It's not going to be 72, because 72 times 72 times 72 is not 216. Okay, dividing by 3 and cube rooting are not the same thing, just like dividing by 2 and square rooting are not the same thing. So we actually have here a little equation. If I solve this equation to get the S by itself, I would need to cube root each side. If I cube root here, this cube root and that cube cancel. I have S equals. When we cube root on the other side, because you always do everything to both sides of an equal sign, the cube root of 216, looking at your chart up above, is 6. Each side of this cube is 6. And I can prove that by taking my answer that I got, 6, and plugging it in. 6 times 6 times 6. Now, you could have also done the same problem just using guess and check. I mean, it's some number cubed. You could have just went 2 cubed. Shucks. 3 cubed. Oh man, 4 cubed. And you could just keep going until you find the right answer. Hey, there it is. S is 216. Guess and check is a valid, good test-taking strategy. It typically is more work, but if you don't have another method for solving your problem, do guess and check. It'll work for you. Letter B. Your friend Frank gave you 32 Skittles and told you to arrange them in a square. How many Skittles would you have to eat before you could arrange the remaining Skittles in a square? Now, this is kind of an open-ended question because there's actually a couple different answers you could have here. If he gave you 32 Skittles, you cannot take 32 Skittles and form them into a perfect square because 32 is not a perfect square. But looking at your chart from up above, we have perfect squares of 25, 16, 9, 4, and 1. Those are all perfect squares. So you could say, well, I'm going to make a square that is a 5 by 5 square. So to do that, I would have to eat, let's see, if I have 32 to get down to 25, I would eat 7 of them. To make a square that has 4 Skittles on each side, we have 4 by 4 is a 16. If he gave me 32 and I went down to 16, I would have to eat 16 of them. A 3 by 3 square would have 9 on each side. If I ate from 32 down to 9, I would have to eat 23 of them. I would eat 28 of them to make a 2 by 2 square. And I don't know if I'd use a Skittle for this because Skittles are kind of round, but a 1 by 1 square, just one Skittle, you could eat 31 of them and then convince him that your one Skittle is a square. But these are all different answers that would technically work. A 5 by 5 square, you'd eat 7. A 4 by 4 square, you'd have to eat 16 just to get down to the correct number of Skittles to make the square. So it's a little bit open-ended. Letter C. This one's one for you. It says your younger sister wants to make wooden block towers in the shape of perfect cubes. She only wants one tower of each size, so all the different block towers can be different sizes, and she has 100 blocks to use. How many block towers could she make at one time with her 100 blocks? Go ahead and pause the video, try this on your own, and we'll come back together when you're done. All right, so I kind of like to work my way up here. So she only wants one block tower of each side, and they have to be perfect cubes. So if she just takes one block, and that's her first block tower, that's going to take one block. Now to make a block tower that is a 2 by 2, and my picture is going to get a little ugly here. There we go. That's a 2 by 2. That's 2 cubed. That would take 8 blocks. So this is 1 cubed, 2 cubed, 3 cubed. This is the last one I'm going to draw because it's going to get ugly here soon. Boom, 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 boom. This one's going to look kind of like a Rubik's Cube. There you go. 3 cubed would have 27 blocks. Now, 4 cubed would have 64, 5 cubed would have 125, but we can't even make one of those because that's more blocks than she even started with. So I'm going to erase him. Now, could she make all of these other ones? I mean, 1 block. She's making one using 8 blocks here. She'll make one using 27 blocks there. Because I don't think she can't even make one using 64 blocks because, oh, yes she can. So she was able to make all 4 of these because that is exactly 100 blocks. She used 1 for this tower, 8 for this tower, 27 here, and 64 there, giving her exactly 100 blocks. So she could make 4 different towers. Four towers. And there's all my pretty work to match up. Letter D says there are 2 numbers between 0 and 100 that are both a perfect square and a perfect cube. What are those 2 numbers? Pause the video, look back at your charts if you need to, see if you can find them, and then when you're ready to continue, hit play, and we'll go through it together. The 2 numbers that are both perfect squares and perfect cubes are the numbers 1 and 64. 1 squared is 1. 1 cubed is 1. So 1 is both a perfect square and a perfect cube. 8 squared is 64. 4 cubed is 64. So 64 is both a perfect square and a perfect cube. Last question. Which of the following irrational numbers is closest to 0? Okay, so this kind of ties in what we were doing before, and I'm still, well, I guess I have been cheating and using my calculator a little bit here. I'm gonna try not to use my calculator here. I'm gonna use my good estimation skills. So the cube root of 9 is very darn close to the cube root of 8, which is about the 2. The square root of 10 is very darn close to the square root of 9, which was about 3. So I'm going to call that about -3. The cube root of 24, -24, would be really darn close to the cube root of 27, which is about -3. The square root of 2 is really darn close to the square root of 1. My perfect squares, 1, 4, 9. He fits in here. He's much closer to 1 than he is to 4. So I'd call that a little bit closer to 1. So this is about 1 times by 3 gives me about 3. So which of these is the closest to 0? 2, -3, -3, or +3? 2 is. And we did not need a calculator. We just needed to estimate. Summary. Without using a calculator, can you give 3 irrational numbers between 5 and 6 that have a value between 5 and 6? Pause the video, give it a shot. I came up with square root of 26, square root of 27, square root of 28, ... the whole way up to square root of 35. Every one of those numbers would be irrational. You could also have said 5.123987391 ... As long as it doesn't stop and doesn't have a repeating pattern, that would work. You could have said the cube root of anything from 126 through the cube root of 215. Those would all be irrational numbers between 5 and 6. So I'm just going to clean up a little bit here. There you go. So anything in this square root range, anything in this cube root range, and then any other just random decimals you came up with that start with 5 point something, as long as they don't stop and they don't repeat. Okay, doing a quick little summary of the whole lesson from beginning to end. Starting with perfect squares are numbers that you can actually take that object and make it into a perfect square. That was actually kind of useful in this lesson. We learned what perfect squares and perfect cubes were. We looked at how you can use a chart to help us estimate the values of square roots by knowing that this square root is close to this perfect square. And I know if I square root 100, I'm going to get exactly 10. So the square root of 96 will be really darn close to 10. And we actually tested a couple using our calculator, even though we weren't supposed to. And we learned we can simplify expressions by doing this same estimation. I knew this piece was about 11, so when I took that times by -2, I get something about -22. We did our first talk on what cube roots are, and we will be doing more talk of that later. But our first talk on cube roots, we learned it is what you get if you take a number times by itself 3 times, and the cube root is the reverse of that. And we estimated just like we did previously by figuring out this number is really darn close to 27, so its cube root will be really close to the cube root of that. Same thing with the expressions, but this time with cube roots. We learned how to solve an equation by doing our square roots and our cube roots. And specifically, we learned that square roots always give us 2 solutions, both a positive and a negative, even though a lot of times we ignore the negative solution. Like when we do Pythagorean theorem way later on in the year, we kind of ignore that there's a negative answer, even though there actually is. More solving, more solving. We did a little bit of problem solving. Understanding again, a cube has perfect cube side lengths, or perfect cube volume. Well, glitchy there. A square can be formed by using square dimensions, and these numbers make all perfect squares. Perfect cubes. We learned there are 2 numbers between 0 and 100 that are both a perfect square and a perfect cube. Interesting. And then comparing numbers and saying which one is closest to 0, and we just did this by estimation. Thank you for watching this lesson, and until next time, toodles.